Hey everybody. Thanks for coming to my lightning talk titled Decentralized Data. My name is Jason Koppe and I'm an SRE at Indeed. I originally joined Indeed as a system administrator and recently my team of system administrators joined the SRE organization. Me and my team have worked on this decentralized data system since the beginning, so I'm just going to share some of our experiences. For those of you who are unfamiliar with Indeed, our mission is to help people get jobs. Our primary product is a job search engine, and that product takes advantage of this system. Quick agenda for the talk. First, I want to give a brief overview of the system. Then I'd like to talk about the toil and outages that we've experienced over the years, and wrap up with some of the improvements and lessons that we learned along the way. So at a high level, what I'm talking about when I say decentralized data is Indeed needed a Lucene search index to power our search engine. And in the early days, we wanted a way to scale the search engine independently from our database. And so we came up with this concept of decentralized data where we would have a Lucene index builder write the data to the file system and then use rsync to ship that data to our application servers, which we could scale independently. And those application servers would access the data that's on the file system and serve the requests. I'm not going to go into all the details about the system. My colleague and I, Julie Scully, talked about this before. So you can find this talk online, how we replicate terabytes of data around the world every day, to learn more about how it works. But I do want to go into some of the toil and outages that we had over the years. So first, the system administration team created this system, the data replication system. And so we were the only people in the company, the centralized system administration team, that managed the stack. And this meant that for any new data artifact that a development team wanted to add into the system, they had to come to the centralized team and ask them to configure replication. And this was okay in the early days, but as the company grew, the system administration team wasn't growing as fast as the development team and caused some slowdowns in getting some data replicated in the system. One of the common outages that we had was a server crash. So you can imagine that we'd have a producer running right now, and in the middle of flushing to disk, the server crashes, and we go to restart the server, and when the server starts back up, the producer tries to resume updating the data, but the data is corrupted, so the producer fails. And in the early days, we manually replaced that data with some known good data. Another common outage was a network disconnection, and this could be between individual servers or in between data centers. So one common problem that happened is there would be a packet loss between two of our data centers or a complete disconnect between two of our data centers. And in this situation, data center 2 was unable to get fresh data. So as a workaround in that situation, we would log in and manually reconfigure the replication path to go through data center 3. And another really common outage that we had was exhausting our network I/O. As we added more and more consumers, the network I/O on the producer server was becoming overloaded. And one of the ways that we got around that was creating what we call a staging tier. So we'd have staging tier servers that would download from the producer server, and then the consumers would download from the staging tier, thus allowing us to have more total network I/O. Another outage that we had was a cascading out of memory during a data reload. So if you imagine that we have a cluster of servers running this application, running our search engine, and they're loading this data artifact version 1. During steady state, we're using about 65% of the JVM heap, and when we go to reload the data, we're using like 95% of the heap. Maybe this is okay, and once we finish loading that version, we can stabilize back at 65%. But the next time we load artifact 3, some percentage of the cluster starts using 100% of its heap, and those instances become unavailable. The remaining parts of the cluster get more requests, and they quickly fall over as well. So this led to a total cluster outage when we were reloading our Lucene search index. So the way that we got around this in that post-mortem was, of course, restarting the cluster, increasing the heap, but we kept part of the cluster having a smaller heap size, expecting that if there was another large data artifact that would come in 3 months or 6 months, that instance would trip and run out of memory first, but we'd still save the cluster. Another outage that we had is we replicated corruption. So the situation was this: the producer file system filled up. There was a bug in the publishing code that allowed a corrupted artifact to be published into the replication system. So it was replicated to all of the servers, and all of the consumers on those servers tried to load this data artifact, but failed because it was corrupted, so they failed their health checks. Great. Then the load balancer took all of those instances out of rotation, and we served an empty page. And this was a total Indeed.com site-wide outage across all of our data centers. So naturally, we wanted some improvements to this whole system, and we started off to create a next-generation system, which we called Reliable Artifact Distribution, or RAD for short. The first thing that we did is we wanted to replace the point-to-point rsync, and we did that with bittorrent. This allowed for a lot more horizontal scalability on the producer server's network, and it also allowed us to kind of automatically have data transfer around these point-to-point data center disconnections. We also wanted the system administration team, now the SRE team, to scale sublinearly to the way that the developers were going. So we made sure that the devs could declare producers and consumers in their code so that the replication system could automatically be configured. And this allowed for developers to add data into the system without needing to come to the system administration team. The next thing we wanted to improve was the canary data reload. So when we had the custom heap size, that was a custom heap size per cluster, per region, per service, and so it just wasn't really sustainable to have all these custom values. So we looked at using console to coordinate the data reload across the cluster. So you can imagine that there's a new version of data available. One instance in the cluster gets a lock and says, hey, I'm going to load this next version of data first. Everybody else just hold on. And once that instance says that it's okay and healthy, the remaining parts of the cluster load that next version as well. Another one of my colleagues, Ann Kilzer, gave a talk about this at Velocity earlier this year, titled Canary in a Coal Mine, so you can find out more about that online. So overall, there are some lessons that we learned through all of this experience. Number one, if you're updating data, always resume from known good data. Your servers are going to crash, and so resuming from known good data is a way to work around that. If you're ever writing to the file system, look into atomic file system operations, because again, these are going to help with crash recovery. The concept of canary is pretty common in release engineering, and it took years of experience for us to realize that having a canary for our data reload was really valuable as well. Use BitTorrent, and build self-service system that your entire engineering organization can use for organizational scalability. That's it. Thanks.